or that influence reaction. So we have the partial ionic character, partial ionic character. We have the partial ionic character of covalent bond. So in the covalent bond, the electron cloud is not static. In the covalent bond, the electron cloud is not static. Let's say, for example, you have hydrogen. It has an electron, alright. Hydrogen, the normal electron, it has only one electron. So and you have another hydrogen, alright. When they come together in covalently, so they share, both of them shared, alright. So this one will donate, alright. Let me use this for this one for this. So both of them will both share. Okay, one atom of this will both share. You get, both of them will both share the electron so that they can form that. So their bond is not actually static. Alright, electron normally there will be some repulsion in between. Okay, but what happens is that it's not static, they move. Get, so that is the logic behind the ionic character. So now let's talk about, let's say we have one hydrogen and we have chlorine. Chlorine is having outermost electron 1 2 3 4 5 6 7 6 7. So you get, so this one is donating. So when both of them share, this one will have this, alright, is donate this, alright. So hydrogen donate this, chlorine from the remaining 8. So both of them will both share. So that is for hydrogen, this is for chlorine, so that they will form that. So you see that now, if you see this very well, alright, both this electron here and this electron, they are both of the same electronegativity. But the hydrogen electron and that of chlorine electron, they are not of the same electronegativity. The electronegativity of chlorine is higher than that of what? Of hydrogen. Now, you can't say that the electron cloud will be closer to, the electron cloud with both of them will be shared, but the electron cloud in HCl can never be the same. Why? Because chlorine is more electronegative than what? Than hydrogen. It will always want to withdraw electron to itself. So that is why you see the electron cloud closer to chlorine side. Chlorine is more electronegative than what? Than hydrogen. This kind of is a covalent bond, but it is what we call polar what? Polar covalent bonding. It's a bond between what? Hydrogen and chlorine. Is a polar covalent. So the electron cloud will be closer to what? To the chlorine, because chlorine is more negative than what? Than hydrogen. What's the electronegativity? Ability of an electron to withdraw electron, ability of an atom to withdraw electron closer to itself in a bond. That is electronegativity. So chlorine is having higher electronegativity than what? Than hydrogen. So it will always want to withdraw electron cloud closer to its what? To its nucleus or to itself. So that is one thing about the characters or factors affecting what? Reactions. So the ionic character is very important. So when an atom involved in bonding are the same, the electron cloud is between them is said to be what? Symmetrically disposed to the two atoms involved in what? In the bond. E.g., these are symmetrically what? These are symmetrically what? Disposed. The electron is symmetrically disposed. But if those are called non-polar bond, covalent bond. This one is non-polar covalent bond. But when we have a polar covalent bond, the electron cloud is not static, is not disposed symmetrically. It will move closer to what? To an atom with higher what? Electronegativity. So that is one thing about that. Do you get the logic now? So the electron cloud will move to the what? To the chlorine side, because it's more what? Electronegative. So what is partial ionic character of covalent bond? One, in the case of covalent bond in HCl, as an example, I've used that one as an example. In the case of covalent bonds formed by atoms that are not similar, is HCl. Alright, where each of the atom is bonding having different negativity, the electron cloud is moved symmetrically, it's not symmetrically disposed. That's what I'm trying to say. In HCl, the chlorine atom is more negative than what? Than hydrogen. And so the electron cloud is displaced towards chlorine atom than that of hydrogen atom. So Schur's bond is said to be non-symmetrical and can be represented as shown below in HCl. This is what I was saying. Alright. So now if you want to show that, so that means we have something like this. Is that okay now? So this is the bond actually. Alright. So now, if that one just represent it, we just represent it by this. partial negative, partial positive. So they call it dipole force of attraction, or they call it dipole moment. Positive, this delta positive and delta what? Negative. So this one will carry delta negative, this one will carry delta positive. So that means HCl, chlorine is more negative than this. Is that okay now? So there is something they call dipole moment. You can calculate the dipole moment of the reaction, but it's not needed, it's not here. So that is one thing about this. Also, you can see that in H2O, all right? So that's why we have H to this and this, all right? So we have partial positive, and partial negative, all right? So it can be two, because this one is having, see that, all right? So that is why it is not symmetrically disposed. So that is one thing about the partial ionic character. So in a reaction process, we always know that chlorine is going to withdraw electron, all right? So for the symmetrical one, let's say you have CO, okay, look at this, it's symmetrical, all right? Partial negative, and partial positive. So this one is symmetrical, because electron cloud is moving toward both sides. Both of them are in different location or reaction process. So the dipole moment for this one will be equal to 0. Is that okay now? Because it is symmetrical. All right. And you know what? When you talk about dipole moment and all that is a force. If you remember your force of attraction, process, or reaction. Okay, let's just leave that. Let's leave that for now. So that is all about the ionic character of covalent bond. Pause. Ionic factor. The electronic factors, or what we call electronic effects. All right, so we have the electronic factors. The effect whereby a non-polar bond, let's say carbon to carbon bond, all right, is polarized because of the polarity of an adjacent or neighboring chlorine. So let's say we have carbon to carbon bond, or we now have an adjacent chlorine. Okay, all right. So this effect is called inductive effect. What does that mean? Now look up. Let's say you have CH3 to CH2 to Cl. All right. Now you know this is electronegative. This will carry a positive charge. Let's look at the carbon inside. Let's consider the major atom, the carbon, the chlorine, the carbon. Is that okay now? The carbon. Is that okay now? This carry negatively charged. All right. This carry positive. This will carry positive. All right. Now, if you look at this effect, we know that there is tendency of chlorine to withdraw electron away from this guy. So the major electron cloud, all right, will be closer to the chlorine because of its nature of electron withdrawing. Are you okay with that? So now there is tendency of chlorine to move electron to its side, all right, so that we have carbocation formed. Abi, it can stand on its own to form a negatively charged. So now this effect actually is called what? Inductive effect. If there is an atom, let's say we have carbon to carbon bond, onto the third carbon or second carbon, we now have an adjacent electron withdrawing group, such as chlorine, or it can be bromine. It can be iodine, all right, electron withdrawing group atom. So you have electron withdrawing group atom closer to the carbon to carbon of simple organic compound like this, all right. The major effect that is reflecting here is called what? The electronic effect or electronic factor, which is called inductive effect. All right. Now, what type of inductive effect is this? All right. This is called negative inductive effect. Is that okay now? So there is tendency of, now look at what I'm doing here, CH3 to CH2 to Cl. Alright, the effect is cumulative, or let's say as this one is one to with electron, the tendency of this bond to move here is very high, because this guy will be very, very unstable majorly when you have chlorine here. Alright, so that is negative inductive effect. Chlorine is withdrawing electron away from this guy, so we are having negative inductive effect. So the cumulative effect of the bond is, let's say we have C to C to C to C to C. Alright, so the effect is more greater here, you get it now. So it will move the bond is moving this way because this one is more connected. So this one will have the effect of the withdrawing power of chlorine on it more than this guy and this guy. So as they are moving this way, all right, so the effect of negative inductive effect is reducing. Is that okay now? Do you get what I'm saying now? So there are some atoms that are click with the carbon to carbon bond or thereabout, so they showcase that fact. So now as this carbon here, this one is serving as negative inductive effect because we're letting electron away from here, but you know this CH3 to this particular center, all right, is serving as an effect. This one is electron withdrawing group. When an atom is withdrawing electron away from the center atom, that is negative inductive effect. But when an atom is supplying electron, all right, that is what we call positive inductive effect. As CH3 is, what should be by as it is here, all right, is supplying, is cushioning the effect of chlorine on CH2. Okay, so as this guy is cushioning the effects of chlorine on CH2, this guy is supplying electron to it. You know, all alkyl group precisely their electron supplier to the showcase what we call the alkyl group. Okay, showcase what we call what? Positive inductive effect. The alkyl group, the electron donor group, showcase what we call positive inductive effect. All right, we have, that means we have two particular effects: the negative inductive effect and what? Positive inductive effect. So the electron withdrawing, when you have electron withdrawing group center like that of oxygen, chlorine, bromine, all right, iodine. So any electron withdrawing group, all right, they will showcase what we call what? It showcase what we call what? Positive inductive effect. Sorry, negative inductive effect. Sorry, please. Negative inductive effect. But that of alkyl group, all right, let's say the amine 2, all right, they showcase what we call what? Positive inductive effect. Are you good with that? So that is that about the inductive effect. All right, so are we right? So let's talk about the characteristics of inductive effect. So inductive effects are permanent effects. Is that okay now? They are permanent effects. Let's say you have a center like this. Looking at this particular center, chlorine is withdrawing electron away from it. Yes or no? That is negative inductive effect. Alright, don't forget, inductive effect also, the positive and negative inductive effect also affect the acidity of a compound. They also affect the what? The basicity of an organic compound. The inductive effect. Alright, so look at, I want you to get this thing fast. They affect the acidity and basicity of what? Of organic compound. For example, when you have a base compound, let's say don't forget also that, okay, they say they affect the acidity and basicity of an organic compound. Now, the alkyl group, or what we call positive inductive effect, all right, they increases basicity of an organic compound, of a basic organic compound. Let's say of a base, or there's a basic organic compound. That means organic compound that are base in nature. For example, amine and so on. Are you okay with that now? So what does it increase? But decreases what? But decreases the acidity of an acidic strength of an acidic organic compound. All right. So, but the negative inductive effect, they are opposite of that. So that means the negative inductive effect, they will surely increases the acidity of an acidic organic compound and decreases the basicity of an organic compound. So you will see what I'm talking about when we continue. Now, I want to start an example here. I said this one is withdrawing electron away from this center, this guy, they are alkyl group. They are supplying electron to it. So what is their effect? Their effect is simply what? Positive what? Inductive effect. They are supplying electron closer to the center atom, where the chlorine we want to withdraw electron away from them. Do you get the logic now? So now for the so I said characteristics of inductive effect. The inductive effect are permanent effects in the ground state of a molecule and are therefore manifested in its physical state, e.g., that is the dipole moment. It occurs only through a sigma bond. What did I say? Alright, that means you have to take note of this. Inductive effect only occur. You can see what I've been doing this morning. Only occur in the word sigma bond. When I say a sigma bond, you can see C to Cl. Alright. So these are sigma bond. Alright. It does not occur in a pi bond. You can't see inductive effect in a pi bond. You know, we have a kind of bond in organic molecule. We have a sigma bond with a single bond, and we have a pi bond. Sigma bond are the strongest of all bonds in organic compounds. Sigma. So we have it in single bond. Alright, when we say a pi bond at the second bond, we have a pi, we have a sigma. You can only have one sigma in a particular bond. It's only occur majorly. You see them in alkane. Example of compound that is majorly just sigma bond involved. Alright, that only have the sigma bond involved at the alkane and so on and so forth like that. It occurs in sigma bond. Alright, we have types of inductive effect. I will explain that. We have negative inductive effects, which is denoted as minus E effect, minus I effect. This is electron withdrawing or electron attracting inductive effects. So you see them in chlorine, NO2, SO3. So the negative inductive effect that you see, minus I effect. Alright, so example are the compound that has chlorine, fluorine, iodine, bromine. Are you okay with that? So also we have the minus O2 group, the CN group, COH group, okay, COR group, alright, COR group. So those are compound SO3H2. So they showcase what we call negative inductive effect. Alright, so you see them. I've already explained that. So those are these. When you say you have C2X, this one is partial negative and partial positive. So this one you always want to withdraw electron to yourself. So we have the positive inductive effect. The positive inductive effect. Alright, so I'm just reading a note out for you, the one that's already been drafted, so that it will be easier. These are electron donating group, alright, or electron releasing group, electron donating group or electron releasing group. Example of groups that shows positive inductive effect are the R. This is the alkyl group, alright. So CH3, that is CH3, C2H5, C3H7, etc. So we have the O minus group, the CO2 group, the CH3, 3C group, and so on and so forth. The effect are shown when you have C to C or C to R. So positive, partial positive, both of them are positive. Where R can be positive inductive effect. Alright, the electric magnitude of inductive effect of alkyl group follows. Alright, so let's say the substituted or tertiary alkyl group, alright, are greater than secondary alkyl group C3. Alright, so I'm talking about positive inductive effect now. So this one will show more of positive inductive effect than this guy. Is that okay? Which is greater than having CH3 then C on this. So you get now. So the effect is cumulative. So the bulkier the effect. Also this, let's say you have C to Cl, Cl. Alright, this one is Cl. It's greater than having just C to Cl, Cl. I'm talking about negative inductive effect now. So you get now. So that is the effect of negative inductive effect. Alright, so that is inductive effect. So when we see some questions, I will just try and use it to let me cite an example of what I was trying to say about the cumulative effects. If they ask you this particular question, that between CH3, CH2, CH2, CH, Cl, and COH, alright, and CH3, CH2, CCl2, COH. They ask which one between, you know, both of them are acidic, they are organic acid. Abi Cl2. So now I ask you that which of these, let's say this is 1, this is 2, which of these is more acidic? You know, I said negative doesn't increase the acidity of an acid. The more it is, the more. So which one would be more acidic? Oh yeah, I give you 1 minute to answer that. So the second one, 2 is more acidic than what? Than 1. Why? Because of we have 2 chlorine here, we have just 1. The more the chlorine, the more inductive effect. It wants to withdraw electron from the center. And you know an acid is what? What is an acid? It's a substance that do what? As Lewis acid. What's Lewis acid? A proton what? Donor. Abi? So that's an acid. Is that okay? So, and this one we want to withdraw electron, so it will have only one more subjected to more protons. So actually Cl2 is more acidic than what? Than this. So that is what I'm trying to say. Alright. Then I'll say we have CH3, CH, Cl, NH2. NH2 is a base. It means precisely it's a base. Between this and this guy, which one is more basic? This is 1 and this is 2. Which of these is most basic? Which of these is most basic? Now if you look at it, 2 is more basic than what? Than 1. Why? Because here we have chlorine, which is negative inductive effect. It will draw electron away from the center and make this guy to be more acidic. So the acidity of this one will be, and if the acidity of a substance is higher than the other one with the same group, so that means the one that is more acidic is less basic. So this is the most basic. Let's say the basic between the two. So this one is more basic than what? Than this. So that is why 2 is greater in basicity than 1. So do you get the logic now? So that those are how the factors affect some organic compounds. So let's talk about the electronic factor. The other electronic factor, which is called the electrometric effect. So here, you know, in the one we just did, now the factor we just did, which is the inductive effect, we talk about the sigma bond or 2. You just talk about sigma bond. Here you can have a pi bond system. All right, so you have to be very, very careful. So this electrometric effect, which is basically the mesomeric effect and the inductive effect, conjugative effect rather. Alright, so this is the effect which involves the complete transfer of a shared pair of electron. Let's say of a shared pair of electron. So this is a sigma bond, because this guy is more negative than this. It always wants to withdraw electron away from here. We have a reagent process, alright, so that we can have this. It's O minus. Okay, don't forget that this one, but withdraw electron, to carry negative charge. You can see the arrow movement, full arrow movement now, full arrow movement. So this is called electrometric. These are effects whereby a complete transfer of electrons is involved. Here, a complete movement of pi bond is what we talk about in inductive effect. But in electrometric effect, a complete movement of pi electron system, of a shared pair of electrons to a particular atom. Alright, to one of the atoms joined by multiple bonds, alright, at the approach of an attacking reagent. So this is that about that. What are they trying to see? Let's say you have RMGX. Now have C double bond O. So this one is coming to this guy. You get, if this one is attacking from here, this one we want to move away. Alright, so that you can have this R to C, okay, to O. This one we're having this and this. No, the bond is already complete. It's only this one that is having negative minus. So it can also attract the other thing that you wanted to. Let's say you have H plus here. So this one can pick up this. So that is the reaction process. So we are just talking about how factors affect reaction. I think you are getting me. Alright, if you get what that, good. So here, the characteristics of electrometric effect is that it is a temporal effect. It's a temporal effect. It's a temporal effect, and the electronic condition of the molecule is restored as soon as the attack reagent is removed. As soon as what? The attack of reagent is removed. It only occurs in multiple bonds and never in a sigma bond. Multiples of bond, it doesn't matter occur. It occurs here in multiples of bond, C triple bond C, C double bond O, C double bond C, and so on and so forth. So you have them like that, like that. So now that is just, this is mesomeric effect actually. Alright. So we have the inductive effect. Inductive effect is this. Conjugative effect. Let's say you have this to this and this. Whenever you have two double bonds alternating between a single bond, it is called mesomeric. It is called inductive effect. It is called conjugative. That is a conjugate. When a double bond is alternating between a single bond, this is a single bond. Double bond is alternating between. That is a conjugative effect. It is called conjugative effect. It can be between C double bond O and C to double bond C. Alright. So these are conjugative effects. This is a mesomeric effect. This is a conjugative effect, and so on and so on. So the bond here can move this way. This one moves this way, so that you have C positive, double bond C, and C negative. Are you okay now? Positive and negative is formed after the movement of bonds. Is that clear now? So that's what we call the conjugative effect. So resonance, let's talk about resonance and mesomeric effect or conjugative effect. This is simultaneous. Let's say in resonance, right, is the movement of, so it's just resonance is just like one of the factors of reaction process of reaction, like thermal reaction of organic, like that affect the organic reactions. So we talk about resonance. So I think the allosomatic effect I will talk about it soon. Alright. So let's just quickly talk about this first. Under resonance, there are some things you have to take note of. It is simultaneous decrease in electron density of one position and the corresponding increase in electron density elsewhere in the same molecule. Alright, so let's say we have this. This guy can come to this side. Why this one will move? What denotes this was this? Look at what we have here. Look at my arrow, that is resonance. So that means we have CH3, C, O, minus, then double bond CH, Abi, then what? CH2 plus. Now, if you look at the total dipole, the total charge here is equal to 0. There is no charge on this compound. But here we have minus, Abi, minus, and also what? Plus. So minus plus alternatively to be equal to what? Is 0. So the charges that you started with must be the charge you are going to end with. This is a resonance reaction process. So there is a displacement of a pi system from here to this side, and also a displacement movement of a pi electron to what? A lone pair. So that is just the process of reactions that we're talking about. And sometimes it can be that a lone pair moves to form a pi, while a pair electron system moves to form a lone pair. So that is one thing about the resonance. Okay, that is one thing about the resonance. So the arrangement of multiple bonds in organic compound, there are two main ways in which double bond or multiples of bond can be positioned in organic molecules. Two double bonds originating as adjacent atoms called conjugated double bonds. Alright, this type of bond depends on one another with electronic interaction between them. Alright, so these are examples of conjugate. Can see this single bond is directly between them. So another example is this benzene. These are conjugative. All the bonds are conjugative. Double bond molecules are separated by just one single bond are called isolated. That, for example, these are conjugative bonds. We have isolated. This is conjugative. We have isolated double bonds. For example, they are separated with more than two or more. This double bond is not conjugated, it is isolated. Also, we have commutated, all right, or we call the allenes. All right, this commutated, there is no separation of double bond, a single bond in between the double bond. You can see that all the double bonds are close together. They are called commutated, or the allenes. So resonance, this is the ability of pi electron in a conjugated system to move in between atoms in a molecule. So it's just oscillation of bonds and all that. So oscillation of electron between atoms with an ion or molecules. Okay. So the definite description of valence bonds, sharing and all that. We'll talk about resonance later. So we'll talk about resonance later. So let's